Welcome to Air Academy Associates series on using SPC Excel. This short video clip will give you the idea of what a confidence interval for a population proportion is and show you how to generate one using SPC Excel. To reiterate what a confidence interval is, it is simply a point estimate that's obtained from sample data, and we add and subtract what is called a margin of error to get an interval estimate. This interval estimate is for an unknown population parameter. It provides an estimate of uncertainty based on the sample data, but associates that degree of uncertainty with a confidence level specified by the user or the practitioner. Sampling, of course, is the act or process of selecting a representative part of a population for the purpose of estimating the true but unknown parameters or characteristics of the whole population. We take elements from the population and we generate a sample. If the data coming from the population is binary, that is, it's a yes or a no, a good or a bad, defective or not defective, we generate as a sample statistic a proportion, and a proportion is a fraction or a ratio. It has a numerator and a denominator. The sample proportion is denoted as P, and it's calculated as x divided by n, where x is the number of elements in the sample that are associated with the category of interest and n is the sample size. This ratio or proportion is the statistic that is used to estimate a population proportion, which is given again as the construct is consistent in a Greek letter, in this case pi. The Greek letter pi is the unknown population proportion for which we want to estimate via confidence interval. Let's take an example where we have a population of voters that voted either yes or no on a particular proposition, and we take a very small exit poll sample of 10. We asked people how they voted, and a no means they voted against the proposal or proposition, a yes means they voted for it. And you can see of the 10 elements here, this is a binary result, yes or no. Of the 10 sample size, 6 indicated that they voted yes. 4 indicated that they did not vote yes, or they voted no, and the proportion in the sample that voted yes, which is the category of interest, is 6 over 10, or 0.6. Now, we show this again just as a means to give you and illustrate the point of how the confidence intervals are calculated. You have a point estimate, P, that comes from the sample, and you have a margin of error that is calculated from P and 1 minus P or Q, the sample size N, and then the level of confidence that we are wanting to choose. So again, I would not use this. This is just demonstration of the technique. I would always use the software. It will give you a more accurate and exact confidence interval. So let's take an example from an office process that processes travel vouchers. And let's suppose a random sample of 120 vouchers were looked at and examined, and they find 12 of those 120 to have errors. So the proportion of vouchers in the sample of 120 vouchers with errors is P equals 12 divided by 120, or 10.10, or 10%. What is the confidence interval for the true but unknown population proportion pi? Well, to get that, we just go to SPC Excel, the analysis tools, confidence interval, and you choose the proportion and binomial in parens. So you have to input 3 things: the sample size, which in this case is 120, the number defective. Now the term defective is still a carryover from the quality world. This could be any category of interest. In the sampling of polling, exit polling, the category of interest was the group that voted yes on the proposal. So 12 out of 120 vouchers were defective in a sense that we found errors, and we want a 95% confidence interval. And if we put those 3 values in, we'll see that The lower limit is 0.0527. The upper limit is 0.168. Sometimes we put these in terms of percent to say the population percentage that has defects is between 5.27% and 16.8%, and we can be 95% confident that that true percentage is somewhere between 5.27 and 16.8. Now, I want you to notice something here that we did not see in constructing confidence intervals for population means, and that is this interval is not symmetric around 0.1. It's a little higher on this side than it is on this side. And the reason for that is the binomial distribution. A binomial distribution is made up of a series of extractions from a binary situation where the outcome is either yes or no, good or bad. In other words, the outcome is binary. And it is not a symmetric, the binomial distribution is not symmetric for all values of p. And in fact, the only value of p for which it is perfectly symmetric is p equals 0.5. So let's reproduce this in the software. So we're going to go to the software now and take a look at that. We've opened up an Excel spreadsheet here, and where we go to get a confidence interval for a population proportion is the analysis tools, and down here to confidence interval, and we select proportion, which is based on the binomial distribution. And then we get our infamous user interface menu that tells us specify the sample size. Well, that was 120 vouchers that were looked at, of which 12 were defective. And if we wanted a 95% confidence interval, the proportion in the sample that's defective is 0.1 or 10%, 12 out of 120. The lower limit is 0.052 and the upper limit is 0.168. So we are 95% confident of what? That the true but unknown population proportion of vouchers that are being processed defective is somewhere between 5.27% and 16.8%. We do not know if it's closer to 16.8% or 5.27%, but what we are confident or 95% confident of is that the true proportion is somewhere between those two numbers. Now let's go back to our example with the exit polling where we looked at only 10. Yes, I realize that that this number is smaller than or bigger than 10, but we had 6 out of 10, and 6 out of 10 voted yes, if you recall. So look at this confidence interval, for example. We are 95% confident that the lower limit, that the true population proportion is somewhere between 0.26 and 0.88. Now that is an extremely wide interval. So how do you make it narrower? Well, sample size is the way you do it. This is a very small sample size, especially for binary data. So if we bump that up, let's multiply everything by 10, and we get 160. 60 out of 100 is still, 6 out of 10, we bumped up 60 divided by 100 is 60%, and our lower limit now is 0.49 and our upper limit is 0.69. So the limits have come closer together, but that was by doing what? We multiplied the sample size by a factor of 10 and the number of defects by a factor of 10, retaining the same sample proportion of defectives, but changing the upper and lower limits. Now what if we multiplied it by 10 again? Made this 1,000 and this 600. Look at how close now the confidence interval limits are. It's 0.57 up to about 0.63. And that's the impact of sample size on a confidence interval for a proportion. Proportions are based on binary data, and whenever we have binary data, sample size becomes a huge factor. A confidence interval for proportions is used a lot in polling for elections. A very common election activity is to determine if your candidate is going to get a certain percentage of votes. So typically the sample size that's out there is somewhere between 1,000 and 1,200. And let's say they looked at 1,168 voters. They asked them their preference. Would they vote for their candidate or not? And let's say 432 said they would vote for their candidate. Well, they can be 95% confident of what? Provided the sampling was representative of the voting population, they can be 95% confident that their candidate is going to pull between 34% and 39 or about 40% of the vote during election time. So this is how you can use a binomial confidence interval for a population proportion. I hope this short video clip gives you an idea. Where you go to get these things are the analysis tools, confidence interval, and proportion. Okay, thank you very much. I hope this was a quick glimpse at generating this type of confidence interval.